Welcome everybody to the second lecture in electrostatic. In this lecture, we'll be talking about a number of topics. We'll be talking about the electric field due to discrete and continuous charges. And also, gonna be talking about the electric field using Gauss's law. The second part of the lecture will be talking about the electrical potential. Then the relationship between the electric field and the electrical potential. So for the first part of the lecture, we'll be talking about finding the electric field due to a distribution of electric charge, either discrete or continuous. For the continuous one, we'll be using Gauss's law. Okay, just as a reminder about the law of the electric field that we concluded last lecture. If we have a point charge located at any place and an observation point at an arbitrary point, the electric field caused by this point charge does have this expression. In this expression, AR prime is the vector from the arbitrary point from the source to destination. AR prime is the unit vector from source to observation. R is the position vector for the observation point, the arbitrary observation point. R prime is the position vector for the point charge. So this is the general expression for electric field caused by a point charge. Last lecture, we said that if we have a number of discrete charges, the electric field is the superposition or the summation. And when we're talking about the field, we are talking about vectorial summation of the electric field caused by individual point charges. So if we have n point charges, the electric field by point charge K equal QK divided by R minus RK prime absolute square. RK prime is the position vector of point charge K. R is the position vector of the observation point. RK prime is the unit vector from point charge K to the observation point. And we have the constant here, and we sum those n vectors to find out the total electric field. So when we have a law like this, it's very important to know what is the meaning of every term in this law and how to apply it, how to express it. And we do this in the exercises and examples that we go through. Okay, so now what would happen if we have sort of a distribution of electric charges, not just discrete charges, a distribution of electric charges. So the most general expression or the most general condition is when we have a volumetric charge distribution. So we have, for example, this, certain volume, and this volume is filled with volumetric charge density. So there is a variation of electric charge distributed within this volume. How would we handle this general case? So this general case is handled by dividing this volume into very tiny small pieces or differential volumetric element, and deal with every single volumetric element as a point charge. So if we have a very tiny volume dV prime, the total charge in this volume equal rho v multiplied by dV prime. Rho v is the volumetric charge density. dV is the volume of this volumetric differential element. Because it's differential, it's very tiny small, we deal with this as a point charge. And remember that we express the charge distribution or the source by the prime. So we denote the region for the charge distribution or for the source by the prime symbol, while the observation point is unprimed. So if we have like such a volume, and this volume includes some volumetric charge distribution, and we want to calculate the electric field at any arbitrary point, we, as I said, we divide this volume into small differential volumetric elements and then sum the electric field from every single volumetric element and deal with the volumetric differential element as a point charge. So this summation, because it's like continuous and it's a very large number of small tiny volumetric differential volumetric elements, is actually the integration. So this expression, when the number goes like very high, goes to infinity, and this expression will deduce to this format. Same constant, summation will be replaced with integration, and we are integrating over the whole source region. AR prime in this context is the unit vector from the differential volumetric element to the observation. Rho is the charge distribution. dV prime is the volume of the differential volumetric element. So rho dV prime are actually the point charge that we're dealing with. R minus R prime absolute square is the same expression as this term. R is the position vector to the observation point. R prime is the position vector to the differential volumetric element. And we are integrating over all sources. So this integration means all the volume that does have source is included into the integration. Similar to here, we are summing over all the available point charges. So if we have discrete charges, this is the expression when these discrete charges coming like closer to each other and the number is going to infinity, which makes a volume of charges. This is the expression as we have explained, and it's very important, very important to understand the meaning of every symbol into this expression and practice how to express it, because I think more than 50% of weight of solving a problem is to formulate the problem right. So here the electric field, because of like a continuous or a volumetric charge distribution, does have this expression. We can also like express it this way, and instead of having AR prime, we can substitute AR prime by the vector R minus R prime, which is the position, which is the vector from the source point to the observation point, and we divide it by its amplitude. So this is the meaning of the unit vector. So this form or that form are equivalent. So whatever is easier, we're gonna use it. So what we have here is we just replaced the unit vector with the vector divided by the magnitude. The magnitude of this vector is the same as this magnitude, so the square will be cubed. So those two formulas are equivalent, or actually they are the same. So in some cases, if the it's very in a general case, this integration is difficult to calculate. So if it's very difficult because the charge distribution is irregular, or the volume where the charge is distributed is like very general and arbitrary shape, it's difficult to calculate it like by hand or in a closed form. So in that case, we can like solve it like numerically, and there is many simulation tools that do this job. But in case of like existence of symmetry, when we have symmetry, if we have a regular shape or like some sort of like a symmetric charge distribution, like the calculation of this integration would be simplified and we can reach a closed form solution for that. Sometimes the charge is not distributed in a volume. Sometimes the charge is distributed on a surface. So we have some surface charge, for example, like on the surface of a ruler, on the surface of a disk, on a like the surface of like some clothes or whatever. So this is a surface and we have some charge distribution. In this case, we can just like modify this general expression for the case of surface. For the case of surface, the charge distribution will be surface charge density. So the surface is divided into tiny small differential surface element. The charge in each differential surface element is rho s multiplied by ds, of course prime because this is the source, and the same thing. R is the position vector to observation, R prime is the position vector to the surface differential element. Sometimes the charges are distributed on a line, like on a wire or something like that. In this case, the charge distribution, like the integration, need to be modified to integrate over certain lengths where we have like the charge distribution. The infinitesimal element or the differential element will be delta L, and the charge on this differential element would equal rho L, the linear charge density, multiplied by dl, of course prime because this is the source, and here's the integration over L prime. I need to adjust this. Okay, so we are integrating here over the whole length of the charge distribution. So those are the three expressions for the three general cases of charge distribution. Charge distribution in a volume, charge distribution on a surface, charge distribution like on a linear shape or like in a line. So let us do some exercises to implement what we have learned. So here, this is, in this example, we are required to determine the electric field intensity. Electric field intensity is the name of the E. Electric field intensity, E, of an infinitely long straight line charge. So we have a line that is extending to infinity and minus infinity, and it does have a uniform charge distribution of rho L, and we want to find the electric field intensity caused by this charge distribution. So here, when we are asked to find the electric field without specifying the observation point, means that we need to pick like any arbitrary observation point. Okay, so the first thing in solving problems is to draw it correctly. So in this case, we just have like infinite line. We're gonna put this line on the z-axis because this is sort of like convenient. If you put it anywhere, you will find it's difficult to express the electric field like at an arbitrary point. So we put the line along the z-axis because this is like sort of like a common axis for like different coordinate systems, and we need to like bring the correct expression. So here it's a linear distribution, so we're gonna use this expression, and the expression here also need to be corrected. So we are like doing the integration over a line. Also, it's very important to choose the coordinate system in a proper way. For wires, the most convenient coordinate system is the cylindrical coordinate system. If you apply this like on any coordinate system, it will be wrong. It will be, sorry, correct, but it might be difficult in one coordinate system compared to the other. So because a wire or like a line, it can be thought of as a very thin cylinder. So cylindrical coordinate system is the convenient one for this. So now, as I said, the first thing to do is to know how to express like the different symbols or parameter in the formula correctly. So dl prime, so we put the line along the z-axis, so dl prime would be dz prime. Anything related to the source would have a prime. Okay, the r prime, which is the position vector to the observation point. So the observation point, to the source point. So the source point is just a differential element on the line where we integrate. So the position vector would be from 0 to this point, which equal z prime az. Okay, so this is the first like r prime and dl. Now we need to express r. R is the position vector to the observation point, any arbitrary point. Because the line is expanding to plus infinity and starting from minus infinity, arbitrary point would be anywhere. If we choose the arbitrary point to be on the xy plane, it would be the easiest for calculation, and this is not a special case. Why? Because if we put the point here instead of like z equals 0, it would be the same thing. Everything is expanding to infinity and minus infinity, so we can just put the xy plane here. There is no difference because we have infinite extension along z. Any point would see an infinite extension of charges in that direction and infinite extension of charge in this direction. So we can put the point on the xy plane, and from symmetry, it's very important here to like consider the geometry. We have two symmetries here. We have symmetries with respect to z. So any point at this z, or let me bring this, any point at this z or that point would see the same thing, infinite extension above, infinite extension below. So there should be z dependency. Also, because this is a line, you can think of a line as a very tiny cylinder. If you rotate the source, you wouldn't see, you rotate the source, which is this line, you rotate it along phi, or around phi, around the z-axis in the phi direction, you wouldn't notice any difference from the position or like from the observation point, which means we must have also the symmetry in the phi direction. So we can benefit from the geometry of the problem in like setting the correct expectation for the resultant field. So, but anyway, let us now like move like systematically. We expressed r and we expressed r prime. The difference r minus r prime would equal RAR, which is the large r from origin to the observation point. It is in the r direction because the point is in the xy plane. R prime, we have it here. So the magnitude of this vector equals the square root of r squared plus z prime square. Very important, this is z prime. So the electric field, because of this element, the differential element, would have this expression rho dl prime, which is rho l dz prime. This is dl. R minus r prime is this expression divided by this magnitude cubed. So the magnitude is 1/2, like half. So cubed is 3/2. So this is the expression of the electric field caused by this differential element. So this differential element is very tiny length. So we deal with it as a point charge. So if we have a point charge here, an observation point here, the electric field will be in that direction. And of course it has two components, one component along negative z, one component along r. So if we consider two symmetric differential elements like this element and the counter element along negative z, so the element along negative z would bring an electric field. Okay, let me erase this. I don't know why it. Okay, so we have a line like this. Okay, so this is the electric field caused by the negative charge or the symmetric point on the line to the differential element. And we can see that this one will have a component along r and a component along positive z, same distance, same position. So the z component will cancel each other and the r component will add to each other. So when we integrate like the dE, we'll have two components, one component along r, one component along z direction. So of course we integrate each one separately. The integration along z, each positive will cancel each negative, so the z component will vanish and we are left only with the r component. So the integration that we have will be along the AR, and the expression is written here. So this integration, when we do it, we'll find that the electric field does have this expression. The z component, the integration along z, will vanish because of the infinite extension and symmetry along z. There is no dependency on phi because of the symmetry along phi. The integration along the integration of the AR component need to be from minus infinity to infinity, which is the extension of the charges, and it is the integration of this expression which will bring this value here. So this is the solution using the integration form for a line or linear charge distribution. So here there are two useful integration pairs that we're gonna like meet frequently, or you're gonna face frequently during our deal with electrostatic, and those integration will be given in the help sheet during the exam. So all what you need is you need to know how to use them. So this is your task to learn or to remember. Of course you learned this before, and you need to practice like the usage of them. So this first one is the one that we use to solve this problem. You can just like do the exercise yourself and apply to find the solution. Okay, moving to another topic, which is Gauss's law. As we said in the previous lecture, Gauss's law is one of the fundamental laws of electrostatic, and it is always valid, but as we said before, it is not always useful. It is useful when we choose the surface where we integrate in a proper way so that we can simplify the solution of the problem. So anyway, Gauss's law specifies that E dot ds, which is the flux out of any closed surface, equal 1 over epsilon naught, the integration over the whole volume enclosed by this surface for rho volumetric charge density dV prime, which equals the total charge inside this closed surface divided by epsilon naught. So in words, the total outward flux of electric field over any closed surface in free space equals the total charge enclosed by the surface. The closed surface doesn't need to be real surface. It can be like just imaginary surface. It can be regular shape. It can be irregular shape. It can take any form of a closed surface. So Gauss's law is always valid, but it is not always useful. So it's always valid. For example, last time we talked about a point charge. If we choose like a cube around this point charge, Gauss's law is applicable, is valid. But we can't use Gauss's law in this case. We can't use Gauss's law with a cube around a point charge to find the electric field generated by this point charge. But if we choose a sphere where the center is at the point charge, we can use Gauss's law to find the electric field. In both cases, Gauss's law is valid, but in the case of a sphere, it is useful and we can use it to solve the problem. The closed surface here, sometimes it's called Gauss's surface. Okay, so let us now practice using Gauss's law in solving a problem. Gauss's law is valid when we can choose a surface where the electric field is normal to this surface and symmetry, like it's uniform along this surface. So if we can define a surface where the electric field is uniform, or the electric field is normal to the surface, or normal and uniform along a closed surface, then we can use Gauss's law to solve the problem. So in the coming slides or coming minutes, we're gonna apply Gauss's law for 3 different cases: a case of a linear charge distribution, a case of surface charge distribution, and the case of volumetric charge distribution. Okay, first example here is like resolving the case of infinitely long straight line charge using Gauss's law. So we just solved the same example using the integration form. Here we are asked to use Gauss's law to solve the same problem. So we have a charge distribution in a linear way from minus infinity to plus infinity, and we want to use Gauss's law to solve this problem. Okay, from the geometry of the problem, as we discussed shortly before, there is 2 kinds of symmetry. Symmetry in the z direction. At any point, we have infinite extension of charges above, infinite extension of charges below. Also, we have phi symmetry, because if we rotate the source, if we fix it any observation point and rotate the source around z-axis or in the phi direction, we wouldn't notice any difference at the observation point. So this is a symbol or a sign of symmetry in the phi direction. So in the z direction there is symmetry, in the phi direction there is symmetry. So we should expect that the electric field is independent of z and is independent of phi, and it must be in the r direction. So from the geometry of the problem, from the symmetry, there is no preference for one angle over the other, so there is no dependency on z. There is no preference for one direction over the other, so there is symmetry with respect to phi. So we must expect, or we must be able to expect, the electric field to be in the AR direction and depends only on R. So now we need to think about how to choose the Gauss's surface. In this case, we said the problem for like a line charge, you can think of this line as a very tiny cylinder. So cylindrical coordinate system is sort of like the first choice to consider. So if we choose the Gauss's surface to be a cylinder with its center along z-axis with this shape, we can start to think about how to apply Gauss's law to solve this problem. Okay, so Gauss's law is stating that over any closed surface, we choose the closed surface to be a cylinder because of the symmetry. E dot ds equals the total charge enclosed by this surface. So what is the total charge enclosed by this cylinder? It's rho L multiplied by the height of the cylinder. So it's rho L multiplied by L, and everything is divided by 1 over epsilon naught. So this closed surface here actually does have 3 surfaces: top, bottom, and side. So the integration here, the left side integration, would be integrated over the top, over the bottom, over the side. So we must divide this integration into 3 parts: one integration at the top, one integration at the bottom, one integration on the side. As we just discussed, the electric field would be depending only on R, and it should be on the AR direction. So on the top, ds equal R d phi dr multiplied by Az. So you must be able to write this expression quickly and correctly. If not, please review the lecture of orthogonal coordinate system. I think it's lecture number 3. Okay, on the bottom, the expression for ds is in the negative because the surface we are talking about is the surface enclosing the volume. So the side that the flux out is pointing out of the volume. So for the bottom, ds is pointing in the negative z direction. On the side, ds is in the AR direction. Its expression is R d phi dz. All of those had been covered in the orthogonal coordinate system lecture number 3. So if you can't write this correctly, quickly yourself, you need to review this lecture. So the electric field is in the R direction. On the top, the ds is in the Az direction. So the dot product will equal 0. You should know why it's equal 0, because AR and AZ are orthogonal. The angle between them is 90, so the dot product is 0. Same thing for the bottom. So the first 2 parts of the integration will vanish, and we are left with only the integration along the side. E is in the AR direction. ds is in the AR direction, so the dot product would be just 1, AR dot AR equal 1. So the integration here will equal ER multiplied by R. E of R means that R is just, E is just depending on R. The electric field along the surface is uniform, the side surface, because of symmetry. So this integration will equal the integration along phi will give us 2 pi. The integration along z will give us L. So the integration will equal this expression. The right hand side is placed here. So the electric field, because of this linear charge distribution, is found. Of course, it is the same expression as the expressions that we got when we solve when we solve the problem using the integration form. And of course, like solving with Gauss's law in this case is easier and faster. And that is because of the symmetry. Second example is using Gauss's law to solve this problem of a surface charge distribution in an infinite planar charge. So we have infinite charge distribution, uniform with surface charge density rho s. So we have infinite extension in this direction, infinite extension in that direction, and we want to find the electric field in this case. So we need to think first which coordinate system to use. Because it's a planar, the Cartesian coordinate system should be our first choice. And we need to think also about symmetry if we want to apply Gauss's law. What kind of symmetry do we have here? So we need to think. So actually we have, if this is x and this is y, we have x symmetry. At any point you see infinite extension along x of the surface charge, and infinite extension along minus x of surface charge. Also we have symmetry along y, infinite extension of surface charge along y, infinite extension of surface charge along minus y. So we have two symmetries along the x and y, and we should expect no dependency on x, no dependency on y, because we have symmetry. So the field must depend on z and must be in the z direction. Also from the top and down, you can also from symmetry you can conclude that at the top the electric field is going in the positive z direction, in the bottom the electric field is going in the negative z direction. So in both cases, top or down, the electric field is going away from the source. So in order to solve this problem, we're going to assume this surface charge distribution is on the xy plane, and we just said that the electric field is going up on the upper side, going down on the bottom side. So now we need to apply Gauss's law. The first thing in Gauss's law to think about is the Gauss's surface. How can we choose like a Gauss's surface? So Gauss's surface can be like a cylinder with its axis along the z-axis, or a cube along z-axis, or a parallelopipe with the axis along z-axis. So this box here is our choosing Gauss's surface. So this box here does have how many faces? It does have 6 faces, top, bottom, and 4 on the side. So the ds on the top, the ds of the box on the top is going up, on the bottom is going down, on the side it's going out of the side, but for the 4 sides it must be parallel to the xy plane. So for the top it's positive z, for the bottom it's negative z, for the side it must be an x and y expression. So here it is in the x direction, here it is in the y direction, here it is in the negative x direction, here it is in the negative y direction. So for all the sides, ds and direction of the electric field are perpendicular. So the integration along the sides will give 0, and we are left up with only integration on top and bottom. So the integration on the top and bottom will equal E dot ds because of symmetry, the electric field is uniform, so the dot product will be just E dot ds on the E multiplied by S on the top, E multiplied by S on the bottom, which gives us 2ES. What is the total charge enclosed by this box? It will equal the area of the base multiplied by the charge density, so it's rho S multiplied by S divided by epsilon naught. Just S will cancel out. The electric field at Z greater than 0 would have this expression. For Z lower than 0, it would have this expression. On the top, it's in the positive Z direction, and at the bottom, it is in the negative Z direction. So using Gauss's law, if we formulate the problem correctly, choose the right coordinate system, choose the correct Gauss's surface, we can solve the problem quickly and easily. A third example is given here. We need to determine the electric field caused by a spherical cloud of electrons. So we have some spherical volume that is occupied by electrons in a uniform way. The volumetric charge equal minus, because it's electron, minus rho naught, and this distribution is bounded by like in a spherical shape, bounded by radius equal b, from the center to origin b, and we need to find the electric field everywhere. So here you can see that we have like a spherical, uniform spherical volumetric charge distribution. So of course you can see we have like theta symmetry, we have phi symmetry, and we must expect that the electric field would be depending only on r and its direction in the r direction. So because of the symmetry, we can think, and of course because it's a spherical charge distribution, we will use spherical coordinate system. Here it's very important to notice that we have two regions. Region 1 from radius 0 to radius b, which is inside the cloud of electrons. Region 2 is for r greater than b, which is outside of this region of electrons, or the cloud of electrons. So inside the source and outside the source. So we need to solve in those two regions. Similar to what we did here, we have two regions above xy plane and below xy plane. Here also we have like two regions inside the volumetric charge cloud and outside the volumetric charge cloud. So we'll solve each region separately. We are using spherical coordinate system, and for the region 1, we're going to choose the Gauss surface as a sphere, radius between 0 and b, and apply Gauss's law. So Gauss's law, E dot ds, the electric field is uniform along this sphere because of symmetry. So electric field also is in the same direction as S. So E dot ds will equal E multiplied by the surface, which is 4 pi r squared. The integration of rho d volume equals the volume of this Gauss's surface multiplied by the uniform volumetric charge distribution. Don't forget the negative sign because the charge is negative charges. Equating the two sides will give us the electric field is in the negative r direction, which should be expected because negative charge, the electric field goes to the electric charge, and the value does have this expression. For region B, we're going to choose another sphere which is this big sphere. Let me do this. For second region, we're going to also choose another sphere of radius equal r greater than b. Applying Gauss's law, the left-hand side will equal the electric field multiplied by the area. The right-hand side, so we are integrating like for the whole volume of the sphere, but the charge just exists up to radius b. So the right-hand side integration will be different than this case. So here for region number 1, the whole Gauss surface or the whole sphere is filled with charges. So the integration would have the volume of the Gauss surface. For region number 2, not all the Gauss surface volume is filled with charge. The charge is filling up to radius b only, so the total charge enclosed would be constant irrespective of r. So the volumetric integration will be from 0 to r, but actually it is 0 after b. So the total charge would have this expression equating the two sides. It will give us the electric field in region number 2, and we would have this shape in region number 1 would have this linear variation of the electric field. Then it will go further, so it increases till it reach radius b, then it starts to decrease as we go further till it reaches 0 and we are at very far from the cloud of charges. So this is the end of part 1 of the lecture, and the remaining part will be in a different video where we talk about the electric potential function.